Today we'll be learning how to convert the limit of Riemann sums to definite integrals and use the definite integrals to evaluate. This is vital in calculus in order to find the exact value of the area under the curve. The limit of a Riemann sum as n, the number of subdivisions, approaches infinity, is equal to the definite integral of a continuous function f over the interval a comma b. So that is the limit of a Riemann sum, which is the limit as n approaches infinity, of the sum of going from k equals 1 to n, f times a plus k times delta x, which is equal to the definite integral from a to b of f of x dx. This formula can be further broken down since delta x is equal to b minus a over n, which would make this formula now the limit as n approaches infinity of the sum of going from k equals 1 to x, f times a plus k times b minus a over n times b minus a over n is equal to the definite integral from a to b of f of x dx. Through the limit of a Riemann sum, we are essentially taking the sum of many rectangles where the width is delta x of each rectangle and the height is the function of the lower bound a plus k times delta x. Once the Riemann sum has been converted into a definite integral, the fundamental theorem of calculus is used to evaluate. The antiderivative is taken of the function through integration rules, and f of b minus f of a is used to find the exact value of the integral. So the integral from a to b f of x dx is equal to the antiderivative of the function from a to b, and that is equal to the antiderivative of b minus the antiderivative of a. And so the integration rules that we're going to be using in these example problems today are going to be constant rule, power rule, and trig rule. So the constant rule is the integral of k dx is equal to kx plus c. And so for the power rule, the integral of x to the nth power dx is equal to 1 over n plus 1 times x to the n plus 1 plus c. And the trig rules are going to be the integral of cosine x is equal to sine x, and the integral of sine x dx is equal to negative cosine x plus c, and the integral of secant squared x dx is equal to tan x plus c, and the integral of secant x tan x dx is equal to secant x plus c. The integral of cosecant squared x dx is equal to negative cotangent x plus c. And finally, the integral of cosecant x cotangent x dx is equal to negative cosecant x plus c. And these rules are expressed as indefinite integrals, but when evaluating for definite integrals, the upper and lower bounds, b and a, will be plugged in for x in order to use the fundamental theorem of calculus to solve. So for the first example here, we have the limit as n approaches infinity of the sum of going from k equals 1 to n of 3 of 1 plus k times 2 over n squared plus 2 times 2 over n. And the first thing that we're going to do is rewrite the general formula, which is the limit as n approaches infinity of the sum going from k equals 1 to n of f of a plus k times delta x, and we're going to match up what we have in the problem. So our a value is going to be 1, our delta x is going to be 2 over n, and then we are going to set delta x equal to b minus a over n and plug in what we have, which delta x is 2 over n, and that is equal to b minus a, which is 1 over n, and the n's are going to cancel, and we're going to be left with 2 equals b minus 1, which will make b 3. And then our definite integral from a to b, f of x dx. We know our bounds. We found b and a, which is 1 to 3, and our f of x. So we could see that the x value is going to be 1 plus k times 2 over n, and the 3 is outside of that x value, and that x value is being squared, and there's a 2 added. So that's why our function is going to be 3x squared plus 2, and we are going to take the antiderivative of this function by using the power rule and the constant rule, which is going to give us x cubed plus 2x at the bounds 3 and 1, and then we're going to use a fundamental theorem of calculus. So f of b, which is 3 cubed plus 2 times 3 minus f of a, which is 1 cubed plus 2 times 1. That's going to give us 27 plus 6 minus 1 plus 2, which is going to be 33 minus 3, which is going to give us 30. And that is it for the first example with the conversion of the Riemann sum to the definite integral, and then the evaluation of the definite integral. For the next example here, we have the limit as n approaches infinity of the sum going from k equals 1 to n to 4 plus k times 3 over n plus 2 times 3 over n. And we're going to write out the general formula again, which is the limit as n approaches infinity of the sum going from k equals 1 to n, f of a plus k delta x times delta x. And we can see that the a value here is 4, the delta x is 3 over n, and then we can use the formula delta x equals b minus a over n, and plug in what we have, which is delta x 3 over n equals b minus 4, the a value over n, cancel out the ends, 3 equals b minus 4, add 4 to both sides, and we're going to get b equals 7. And then the definite integral is from a to b, f of x dx, and we have a and b, which will be 4 and 7. And then our x value of the function is 4 plus k times 3 over n, and there's a 2 on the outside and a 2 added, so that's how we know that our function will be 2x plus 2 dx. And then we are going to be using the power rule and the constant rule again to take the antiderivative of the function, which will be 2x squared over 2 plus 2x at the bounds 7 and 4, and the 2's are going to cancel and leave us with x squared plus 2x at 7 and 4. Then we're going to be using the fundamental theorems of calculus, and f of b will be 7 squared plus 2 times 7 minus f of a, which is 4 squared plus 2 times 4. That's going to leave us with 49 plus 14 minus 16 plus 8, which is going to be 63 minus 24, which will be 39. And that is it for the second example. And next over here with this third example, which is the limit as n approaches infinity of the sum going from k equals 1 to n sine of k times pi over n plus 2 times pi over n. We are going to start by writing out the general formula as always, which is the limit as n approaches infinity of the sum going from k equals 1 to n, f of a plus k times delta x times delta x. And there is no a value here, but there is our delta x over here, so we're going to use the formula delta x is equal to b minus a over n, and our delta x is pi over n equals b minus 0 because there is no a value over n. The n's are going to cancel and b is going to be equal to pi. Then our definite integral from a to b of f of x dx, and the bounds are going to be from 0 to pi. And for the function, the x value is k times pi over n. There's a sign on the outside and an added 2, which means that our function is going to be sine of x plus 2. And then we are going to take the antiderivative, and the antiderivative of sine of x, we have to go back to the trig rules, and as you can see here, the antiderivative of that is negative cosine x. So we're going to be using that and the constant rule for this problem, and that is going to give us negative cosine x plus 2x at the bounds from 0 to pi. Then we're going to be using the fundamental theorem of calculus, which is going to be f of b, which is negative cosine pi plus 2 pi, minus f of a, which is a negative cosine of 0 plus 2 times 0, and that is going to give us 1 plus 2 pi minus negative 1, which is going to give us 2 pi plus 2, which is also equal to 8.2831. And that is the last example here. So all of these problems were my own examples, but example 1 was inspired by the writing and interpreting Riemann sum circuit, and examples 2 and 3 were inspired by the definite integral and limit of a Riemann sum AP Calculus Workshop worksheet by Gary Taylor. Hope you learned a lot from this lesson. Bye!